All right. Good morning, good afternoon, good evening. We're returning here back to our lecture into Chapter 5, 5.2 and 5.3 and 5.4. And so we left off talking about the conditional probability here and how we can look at this probability to establish whether or not two categorical variables are independent or if they're dependent or associated somehow. So in the previous video, we found that party affiliation and willingness to accept refugees, that those are definitely dependent. Republicans were the most likely to not accept the refugees, whereas Democrats were the least likely to not accept the refugees, and independents were right in the middle. Okay, so in this last example that we did, we showed two events which are independent, meaning given the card is diamond, that doesn't give me any more information on the likelihood of the card being an ace. So what we're saying here is that given this information, it doesn't help in determining the chances of getting an ace. So remember what this means. It's saying probability of card, the card that we select is an ace, given, this vertical line bar means given, that we know already that the card is a diamond, right? So we know the card is going to be a diamond, and we want to know what's the chances of that card being an ace, right? And so if this is true, if this probability, this conditional probability is equal to just this what they call marginal probability, we say this is just probability card is an ace. Okay, so in here we're selecting really out of the 13 cards, because we know it's a diamond and there's 13 diamonds, so really we're just selecting out of those 13 cards, whereas here we're selecting out of all 52 cards. Okay, so these events are independent if they are equal to each other here. Okay, so just note that we could have reversed this. We could have done probability of card is diamond given card is ace is equal to probability card is diamond. We could have done that as well, but it is sufficient just to show one. Okay, but if this were true, okay, if these are actually equal to each other, and if we were to flip the order here, we get the same thing. But anyways, we say probability card is an ace. There's 4 aces out of the 52 cards. We could reduce this down, write it as a percent, decimal to percent. Here we're saying probability card is an ace, given card is a diamond. Well, that's just, we only have 1 out of 13 to select, so we get the same result. Okay, so the reason I review this is because we're going to extend this rule out for more events here. Okay, so what we get into here are what we call independent events and the multiplication rule. So it says outcomes of several coin flips are usually considered to be independent, right? So it says suppose we have a fair coin and flip 3 times. What is the probability that all 3 are heads? So what they mean by the coin flip here is that, okay, so what we're saying is that, well, the first coin flip is a heads, and the second coin flip is a heads, and the third coin flip is a head. So these ands are important because remember, it's kind of where they overlap. So it's just saying that the ands are guaranteeing that all 3 happen at the same time. Okay, we get heads and heads and heads. All 3 have to be true. So so here we just extend out and add an extra and because we have an extra event. So we add the and here. So really what we're talking about here is these outcomes. The outcome, we're saying, what's the probability heads on the second coin flip, given that, the first one was heads. They're independent, right? What's the outcome of the third coin flip, right, is independent of what happened in the first and the second. So really, these outcomes are independent, right? They're the result of each coin flip, the results are independent of each other, right? So what we're using here is this rule here. We're saying, okay, well then that's just probability of heads on the first, probability of heads on the second, probability of heads on the third. Now, the rule that we're using there is this rule here. The multiplication rule. What is that? So, so remember we had these conditional probability definitions here, and from these definitions we got a brand new definition for the AND probability. So in these AND probabilities, we're multiplying, these two probabilities here, So that's the multiplication rule. It gives us another method for finding this AND probability. Now, if these events are independent, then this condition disappears, and we get this result here, right? So we get probability A and B is equal to probability of A times probability of B, and so that's the other form of the multiplication rule if A and B are independent events, right? So this is like coin toss 1 heads and coin toss 2 heads. Well, that's just probability of just heads and probability of heads, pretty much. Okay, so we're going to extend these rules out, but now imagine probability of A and B and C and D and E, so we're going to extend this rule out to more than 2 events, but they're all independent. And at the very end of our talk, we'll visit this multiplication rule, where they're not. Okay, but typically, flipping coins and rolling a die, those are considered independent events. So in this example, of course, we have a fair coin, and we say since independent, and so we get 1/2 times 1/2 times 1/2 is equal to 1/8. Okay, because that's probability of heads, fair coin, and that would be 12.5%. So that 12.5% says, well, there's a 12.5% chance that if you were to flip a coin 3 times, all 3 would be heads. Okay. So that's what we get there. Say if the coin were not fair, say it was 1/3 chance of heads, then it'd be 1/3 times 1/3 times 1/3. Okay. All right. So here we're just extending out that multiplication rule. So in this example, I'll just give you something else to look at, but we're just saying outcome of several rolls of the die are considered to be independent, right? So it's just kind of like a coin flip, but now we have 6 possible outcomes. So it says, suppose we have a fair die, and we roll it 10 times. What is the probability that the first 5 rolls are a 1 or 2, and the last 5 rolls are either a 3, a 4, a 5, or a 6, right? So I'm just saying event A includes the outcomes 1 or 2. Event B includes the outcomes 3, 4, 5, or 6, right? So one thing to note about these 2 events is that they are mutually exclusive, right? They do not share any outcomes in common, and they are also complementary, meaning that if you were to look at A, all the outcomes in A and all the outcomes in B, right? If you put them together, you get the entire sample space, meaning all the outcomes that are possible for the die, right? So the B here is really like an A complement, right? In the previous example, the tails will really be like heads complement, okay? But anyways, so what it means pretty much, so I kind of jumped to it here, but we're just saying, well, that's the probability of 1 or 2 and 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 3, 4, 5, 6 and 3, 4, 5, or 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 6. So each of these rolls of the die are independent, so that's why we get the product of these. They call them marginal probabilities. Marginal just means there's no and or, they're just one event, that's it. All right, but since they're independent, we just look at the product. So probability of 1 or 2 is 2 over 6, 1 or 2, 2 over 6, and we have this 1, 2, 3, 4, 5 times. And then of course we have probability of a 3, 4, 5, or 6. So that's 4 over 6 times 4 over 6 times 4 over 6, 5 times. Right, and if you do that, you would get, so remember I'm converting to percent here, but that's like, your decimal will be 0.005 with some more decimals there, but I convert it to percent, so we get 0.05% chance of this occurring, okay? So now, so really quick before I come back, just before I leave here, just notice here that I'm telling you that the first 5 are 1 or 2, and the last 5 are 3, 4, 5, or 6. So I give you the order, right? First 5 are 1 or 2, last 5 are 3, 4, 5, or 6. If I would have just said, what is the probability that any of the 5 rolls are 1 or 2, and the other 5 are 3, 4, 5, or 6, that probability is much more difficult to count, to keep track of, because then we have to keep track of all the different possible combinations in which we get 1 or 2 out of the 10. But that would be something we do later. So in this example, we're just applying it to some other context here. We're just saying Florida's recidivism rate is 33%. This means that about 33% of released prisoners end up back in prison within 3 years. So suppose 3 randomly selected prisoners who have been released are studied. Okay, and of course here, in order for us to use the multiplication rule, let's just assume each outcome is independent. Okay, so each prisoner more or less has the same chance. And the outcome of each prisoner is former prisoner are independent of each other. Okay, so hopefully, I guess maybe they don't know each other, right, or something like that. Okay, but anyways, so now we ask, what is the probability that all 3 go back to prison? Okay, so it's just kind of like a coin flip now. Okay, where going back to prison is heads and not going back is tails. Okay, so we say all 3 go back to prison is just kind of saying, like, you flip a coin 3 times and all 3 are heads. Okay, so here we would get, remember this is percent, so I have to convert it to decimal and doing the math, but I get 0.33. This is probability prisoner 1 will go back, and probability prisoner 2 goes back, and probability that prisoner 3 goes back. And since they're independent, we could just take the product of these probabilities. So I just shorthanded this. I just wrote this as a 0.33 cubed, but roughly you get 3. This is a 3.59% chance that all 3 prisoners will go back to prison. Okay, so now we can ask, what is the probability that all 3 do not go back to prison? Okay, so here it's saying that each of them, so in terms of like the coin flip problem, is kind of saying what's the probability that you do not get any heads. So it's the same as saying what's the probability that you get all tails. Okay, so what this is saying is what's the probability that all 3 do not go back to prison. So either you go to prison or you do not go back to prison. Right? So do not go back to prison is the complement of going back to prison. Right? So if I want to find out what's the probability for a single individual not going back to prison, well, that's a complement. Right? So I just do 1 minus this quantity here to get 0.67. Okay, now what this represents, this is probability of not going back to prison. This is for prisoner 1, and the probability of not going back to prison for prisoner 2, and the probability of not going back to prison for prisoner 3. Since they're independent, we could just multiply these out and we get 0.67 cubed, where 0.67 is just the probability of not going back to prison for a single person, right? And so what we would get here is roughly a 30.1% chance that all 3 prisoners do not return to prison. All right, so now in your book they focus on these 2 key terms, such as at least 1 and at most 1. And so what they're referring to is if you see an at least 1 or an at most 1 within the question of probability, you're advised to use a complement to find this probability. Okay, so in this next question here, they're asking what is the probability that at least 1 returns to prison. Okay, now what does at least 1 mean? And I mean, I know that you know what at least 1 means. Okay, I'm not here to like insult your intelligence or anything like that. Okay, But for some reason in probability, I mean, students always mix it up, okay? I mean, I've witnessed this all the time at UCSB. Doesn't matter what level of class I was teaching, but it's just one of those things. But if once you understand at least one, the thing is that we want to use the complement because it's just much faster to do, okay? So here, in this case, at least one, it means either one of the prisoners returns to prison, or 2 out of the 3 return to prison, or all 3 return to prison. So what that means is, I would have to, for each outcome here, 1, 2, or 3, I need to find the probability of each of those events occurring. Now, we already did 3, okay, which was 3.59%, but how would we do 2? And so it gets a little trickier because in the previous example, I'm telling you, well, this is how I had the first 5 are 1 or 2, the last 5 are 3, 4, 5, 6. I'm giving you the order there, right? So in this example here, in this here, when we say two prisoners returning to prison, well, which of the 2 is it, right? Is it the first 2, the last 2, or the first and the third, right? So we have to take into account all those combinations, right? And so we're not quite equipped for that just yet in this class. So what we could do is really, I mean, as far as the number of prisoners that can return to prison, what are all the possible numbers that we can see? Well, it's either 0, none of them return, 1, one of them returns, 2, 2 of them return, or 3, all 3 of them return. All right, so if we want to look at, so the total outcomes are 0, 1, 2, 3. So if we want to look at least 1, well, probability of at least 1 is equal to 1 minus the complement of at least 1, right? So at least 1, so what number do we exclude? 0. Okay, 0. Right? So what happens here is this is probability of at least 1 prisoner returning to prison is just equal to 1 minus the probability that none return to prison. And we already found that probability right here. Okay? So this would be 1 minus, of course I have to convert it to decimal, right? I have to convert it to decimal. It would be 1 minus 0.301, which should give us a 69.9% that at least 1 will return to prison. Okay, so in the book, I encourage you to check it out there, how they use at least 1, but they're just saying, yeah, this is the trick for that there. Now, the other thing they could do is at most 2. So at most 2 means either 0, 1, or all 2, or really, or 2, or 2 return to prison. Okay. And so what's the complement of at most 2? Well, that's just 3, right? That's the one we excluded. So if we want to find the probability of at most 2, well, that's just 1 minus the probability that all 3 return. Okay, and that's just by complement. Okay, so here I would do 1 minus 0.0359 because that's what we found previously, and we get roughly a 96.41% chance that at most 2 will return to prison. So either 0, none of them return, or 1 of them, or 2 of them. Okay. In the previous 3 examples, we were using the multiplication rule for the AND probability, where we have independent events, and then of course we wrapped up with just a common probability trick in dealing with at least and at most probabilities, where we use the complement to make life a lot easier. So now, very briefly, I want to get into where we use a multiplicative rule where the events are not independent. Okay, so I just want to introduce this topic of the false positive. Okay, so the false positive false positives are referring to maybe tests. So for example, you apply for a job, and then they drug test you, and then they give you a call and say, hey, guess what? You tested positive for all of these drugs, right? And you know for a fact that you don't do drugs, right? So the reality is you never use drugs, but the test is saying you did. Okay, it's a false positive. Or, for example, the Central Park 5, right? And there's a documentary out on Netflix, right? So the court or the jury, the test, right? They came out and said, yeah, you 5 are guilty, right? And that's really what happens in the courtroom. It's like that's like a test, right? But a lot of times we don't know what actually happened, but we make the decision based off the data presented, right? So I mean, the test there was like the jury in the courtroom, and they said, okay, you guys, you 5 are guilty, but in reality they weren't. Okay, that's a real bad false positive. And even when you go into the doctor's office, and a lot of their tests give false positives, but usually what they do is a backup test that's a little bit more expensive. Okay, but they use that to avoid these false positives, right? Because they don't want you walking out of their doctor's office thinking you're thinking you're pregnant when in actuality you're not, right? Or vice versa. There's false negative, right? They say you're not pregnant when in actuality you are, right? So anyways, so these things are more common than one may think, okay? But a lot of the decisions we make, we don't know 100% true if they're the right one, okay? And this happens a lot. So let's do this example here. Okay, so imagine you're there on the intersection of Collins and College Park Drive. I don't know if I have the intersection right, but the intersection where everybody tries to blow the yellow light. Okay, all right. But anyway, so imagine you're out there at night, maybe walking towards Starbucks, and you witness a hit and run accident. Okay, you witness a hit and run accident. So someone's crossing the street there. Someone's once again trying to get past that yellow light, and they hit someone. Okay, and well, let's not say it's you. Just say it's some witness. Okay, but someone witnessed this accident, and they're the only witness to the accident that night. Okay, but they say it was hit by a taxi cab. Okay, so in Moore Park, let's just assume that there's 2 taxi cab companies. Okay, there's a blue taxi cab company and the green taxi cab company. Okay, so this was nighttime, right? This was nighttime, and the witness is gonna come out and say which color they thought it was that night. So in this hit and run, the 2 as far as the taxi cab companies, there's only green and blue, and 85% of them are green, and 15% of them are blue. Okay, but our witness comes in and says the taxi cab is blue, right? So remember, these are like anecdotes, right? These are like anecdotes, and they're weighed heavily in the courtroom. And so the thing is well, how much do we believe this witness here, right? How should we believe them, right? What's their credibility? Is there anything we can do in the courtroom to measure their credibility, right? Because we don't know who they are, right? We don't know who they are, and they were just, all they do is say it was blue, and it was dark that night, and maybe blue and green look similar at night. I don't know. But how do we test the reliability of this witness, right? In an unbiased approach. So what we do in the court is we could do this. We can go back to that intersection and shut it off for the night, and really shut it down when the conditions were similar to the night of the accident. Okay, and so what we'll do is we want to test the reliability of the witness under the same circumstances that existed on the night of the accident. Okay, and so what we do here, so it says here, we conclude that the witness can correctly identify the color of the cab 80% of the time. So what we're doing is we have the witness stand exactly where they were the night of the accident, and then we say, all right, send the blue one, send the green one, send the blue one, send the green one, the taxi cab, send the blue. Okay, now blue, now green, now green. And we do this over and over and over again, right? And have them drive the same way they were driving on the night of the accident. And what we do is the witness is just writing down the colors that they see, the colors that they see. So say we sent 100 blue and 100 green cars. So we know the color, right? So what we find is that 80% of the time when the taxi cab was blue, okay, the witness said blue 80% of the time, right? So they matched up. But by complement, what that's saying also is that 20% of the time when the taxi cab was blue, the witness said green, right? So if we're looking at 100 blue taxi cabs, 80 of them they guessed correctly, and 20 of them they didn't. And this happened the same for the green, right? So 80% of the time when it was a green taxi cab, the witness was able to guess correctly. Okay, so this percent here is actually a conditional probability, right? It's probability a witness says blue, given that the taxi cab is actually blue. Okay, all right. So here we want to find the probability that the cab involved in the accident was actually blue, given that the witness has said blue. Now, fortunately, this probability we won't be able to find. Given that it's limited by the book, so I'm not going to have us cover it. But really, this is the probability we want. But but we'll save that one for later. So really quickly, I just want to set up these events here, just as far to work on my notation. So green and blue, that's like the reality. Okay, in reality, the taxi cab was green, and in reality, the taxi cab was blue. Right. So this is like, for us, in reality, the subject used drugs. In reality, the subject didn't use drugs, And then here's like what our test says, right? The test says we use drugs. The test says we don't use drugs. Okay, something like that, okay? So here, our test, here's the witness, okay? So WB is the witness says blue. WG is the witness says green, okay? So just really quick, as far as like what a Venn diagram would look like in this experiment, it would look very funny, but we could break it up into 4 pieces. So in this example, so really here, this intersection here, it's a and, okay? It's an and. I just forgot that there. Okay, that's a and. Okay, so you see these signs here, they're called the intersection signs, and they represent the and. Okay, but in this case, we have a witness says blue, and the taxi cab was actually blue, right? So this means that the witness decision lined up with the reality, right? Or a drug test lined up with the reality. Okay, this is saying witness says green and the taxi cab was blue. So in this case, our test does not match up. So this is what we call like a false negative, right? It says it wasn't the blue one when in fact it was. This one here says witness says blue and it was actually green, right? So this is what we call a false positive, right? It's saying it was the blue one when in reality it was the green, right? And this is another thing here. This is witness says green and it was green. So this means, once again, our witness testimony matches up with the reality. So one thing that we do is we create these probability trees to help organize all of the probabilities that were given in the problem. So what I have here is all taxi cabs, right? And then I split them up to blue and to green. So within blue, there's 15% blue, and within green, there's 85% green, right? These two events, they're obviously mutually exclusive because we don't have a taxi cab, they're both blue and green, and they're also complementary. Okay, if you were to put the blue taxi cabs with the green taxi cabs, you would get all the taxi cabs. So now we're using these conditional probabilities, right? Because so this is the land of blue taxi cabs, right? So this sample space right here is just blue taxi cabs. So within the blue taxi cabs, given that it's a blue taxi cab, what's the probability that the witness says blue? And that's what this is doing here. So given that's a blue taxi cab, what's the probability that the witness says blue? Well, that's 80%, right? Because they guessed correctly 80% of the time. Now, what's the probability that witness says green, given that it was blue, right? Well, these are complements of each other, because either witness says blue or witness says green. So in this case, we get 20% chance of getting it wrong. Okay, and then we do the same here. Here's the land of just green taxi cabs. So this is probability that witness says blue, given that it's green. So they guessed wrong, they made a mistake. We know that's 20%. And what's the probability witness says green, given that the taxi cab was green? That's correct, so that's 80%. So here, this tree allows us to make a real nice, to help us organize all of our probabilities. And it's really clear that these are, mutually exclusive and disjoint, and that these are conditional. Okay. So just to list these out, we're saying, well, here I have probability blue is 0.15, probability green 0.5. So I have all my probabilities listed out nice and neat, and I have my conditionals listed out nice and neat. Okay, so here we want to find the probability that the witness says it's blue, taxi, cab, and in reality, the taxi cab was involved in the accident. Okay, so here we want to find probability witness says it was blue, and in reality the taxi cab was involved in the accident, right? So this is in the top left corner of a Venn diagram, and we just want to know what are the chances of this both being true, right? So to find this probability here, I have to use the multiplication rule. Okay, so I have to find which of these can I piece together to find it, right? So here I have witness says blue and blue, right? So witness says blue and probability of blue. Well, that's just 0.80 times 0.15. We get 0.12, which is 12% chance. Okay, so there's a 12% chance that the witness says blue and it's actually blue. And we ask, do you believe the witness? And given this, of course not. It's very small. It's very small. Okay, so and so that's where we end it. Okay, it's very small, but really what's of interest here, and the book sells us short, okay, a little bit here, because this number is really misleading, because we should really be conditioning, and the reason is that they're just showing these examples to you for the sake of showing this multiplicative rule, which is cool. Okay, but one thing to note is that this percentage is very small. And the reason is think about it. Probability of blue is very small, right? The proportion of blue taxi cabs is very small, right? And the proportion of green is very large relative, right? So this probability is going to be very small. This is like if you randomly select an outcome, right? What's probability witness says blue and is blue? Well, right away, witness says blue is blue taxi cab is very small right away, right? So our probability is more likely to be small. Right, so a little bit misleading, but what we really would be after here, is this probability. Sorry. Well, really, we want to reverse the condition. We want to know probability of blue given witness says blue. Okay, that's really what we want there, right? Right, because in reality, what these are saying is we already know what the taxi cab color is, right? Because we're simulating it, and then we're saying how likely is our test to match it. So it's just like if we were to have, we have 20 people, we know they use drugs, and we have another 20 people, we know they don't use drugs, and then we test them, right? And so really, what's the point in testing if you already know? But we want to know how well our test holds up, right? How many times will our test correctly guess? Right, but in reality, if I switch these, right, if I switch these two around, well, what this is saying is, what's the probability? What's the probability that the taxi cab was actually blue, given that the witness says blue, right? And so when you reverse the order of these, they're not the same. Okay, they're not the same. So even in terms of the drug test, really, when our applicant comes in, we don't know if they use drugs or not. We don't know. All we have is the test, right? So given the test, how likely is it that they actually use drugs? That's really what we're interested in here, right? So in this problem, we would really keep going. We keep going, right? We wouldn't stop here because this is misleading. But here, we want to know what's the probability that it was actually blue given that the witness says blue, okay? And so to calculate this probability is a little tough, all right? Because we have a formula for calculating this, okay, but we need a little more, and I think that part is maybe they think is beyond the scope of the class, so they don't cover it. But if I've actually done this problem, and I'll tell you that it's equal to 41%. Okay, so I did this number already. So so before the witness, okay, if the witness wasn't there, what are the chances that it was a blue taxi cab? Well, 15%. Okay, and then the witness comes in. And they're like 80% reliable, right? We test them under simulations, they're 80% reliable. Okay, so we have this witness who's 80% reliable. So let's update this probability of blue given that the witness says blue, right? So we say now what are the chances of the taxi cab really being blue when we update it with this witness testimony? Well, it increases from 15%, but it only goes to 41%. Right, so what it's saying is that, okay, this witness who's 80% reliable said that the taxi cab was blue. What are the chances that it was actually blue? And it's only 41%, right? So based off this number, we definitely would not take the witness's testimony anywhere. Okay, pretty much we would throw it out based off these numbers. Okay, but I just wanted to mention that there because really this is where the money's at. Okay, this is where the decisions are made. Okay, but how we calculate this, it's a little tougher, and we'll just save that for later. Okay, but anyways, that ends this talk, and we'll see you next time in finding empirical probabilities.